A critical zero-day vulnerability in a core Google Cloud API was recently discovered not by a team of elite human researchers, but by an autonomous LLM agent. For years, traditional DAST tools and human bug hunters missed a complex business logic flaw within the OAuth 2.0 implementation because they couldn't see the nonlinear relationship between secondary authentication tokens and administrative metadata. The AI agent, however, performed recursive chain-of-thought reasoning, simulating thousands of edge case interactions in seconds. It didn't just find a bug, it understood the systemic weakness of the architectural design. This marks the end of the security by obscurity era. When attackers utilize GPU clusters that never sleep, the traditional perimeter defense model based on human speed response becomes a liability. We are witnessing the birth of autonomous exploitation, where the time to exploit is shrinking from months to milliseconds. By the end of this lecture, you will understand the exact framework needed to architect a defense that doesn't just block attacks, but anticipates them through machine learning resilience. To survive in 2026, security leaders must move beyond reactive patching. The strategic decision facing every organization today is how to implement a proactive AI defense that mirrors the capabilities of the attackers. This involves integrating reachability analysis and AI-augmented red teaming directly into the DevSecOps pipeline. We aren't just talking about better scanners, we are talking about autonomous defense systems that can simulate their own vulnerabilities and deploy virtual patches before a human even sees the ticket. This paradigm shift requires a fundamental change in how we view the perimeter. It is no longer a static wall, but a dynamic, self-healing fabric. In this course, we will define the AI resilience framework, providing you with the decision-making criteria to determine which AI security tools are essential and which are mere hype. This is the only way to counter machine speed discovery with machine speed protection. But how do we actually arrive at this point of total automation? In the next chapter, we will trace the evolution of vulnerability research from manual code review to the era of the autonomous hunter. In the early days of security, vulnerability research was a purely manual craft. Security researchers spent weeks staring at assembly code or C++ files, looking for buffer overflows or format string vulnerabilities. By the 2010s, we saw the rise of fuzzing tools like American Fuzzy Lop, AFL, and Peach Fuzzer, which revolutionized the field by automating the generation of malformed inputs. However, these tools were fundamentally dumb. They relied on genetic algorithms or predefined templates without understanding the code's actual purpose. As systems migrated to microservices and complex cloud-native architectures, the sheer scale of modern codebases rendered manual review impossible and traditional fuzzing highly inefficient. The industry hit a ceiling where the cost of finding a zero-day was skyrocketing because our tools couldn't keep up with the complexity of modern software. We were essentially throwing millions of random inputs at a wall and hoping for a crack. But why did these powerful tools still fail to catch the most devastating logic flaws? The answer lies in the lack of semantic awareness, a gap that was about to be bridged by a new generation of intelligence. This transition from blind automation to informed reasoning is what defines our current era. Question: can we ever move beyond simple pattern matching to true understanding? Let's see how the paradigm shifted. Traditional scanners, such as standard SAST and DAST tools, operate on a signature-based philosophy. They look for dangerous functions like strippy or shell exec and flag them. This leads to the infamous false positive fatigue, where security teams are buried under thousands of irrelevant alerts. In contrast, AI-driven research utilizes semantic context. Instead of just seeing a function call, an AI trained on security datasets understands that a specific variable is user-controlled and flows through a series of sanitizers before reaching a critical database sync. It evaluates the intent of the code. In 2026, we are seeing tools that don't just find bugs, they prove them by generating a working proof of concept, POSI. While a legacy scanner might flag a potential SQL injection, an AI agent will actually craft the payload, bypass the BOAF, and demonstrate the data exfiltration path. This fundamental shift from syntactic checking to semantic reasoning is why modern bug bounties are being dominated by AI-assisted hunters who can filter noise at a speed no human can match. Payoff: this shift from pattern matching to intent analysis leads us directly to the engine powering this change, the LLM and its reasoning capabilities. The real breakthrough occurred with the release of reasoning-optimized models like Claude 3.5 Sonnet and the GPT-4o series. Unlike previous iterations that merely predicted the next word, these models function as reasoning engines. In the context of security, this means the ability to chain vulnerabilities. A human researcher might find a low-severity IDR, insecure direct object reference, and a minor XSS, cross-site scripting, and ignore them. However, a reasoning engine can hypothesize a path where the IDR is used to leak an administrative CSRF token, which is then delivered via the XSS to gain full RCE, remote code execution, on a server. This chain discovery was previously the domain of elite human hackers. By 2025, AI agents began systematically testing these hypotheses across entire SaaS platforms. They don't just see a single bug, they see the graph of potential exploitation. This reasoning capability allows the AI to act as a force multiplier for bug bounty hunters, turning a single observation into a catastrophic exploit chain within seconds. Teaser, but how does the AI manage to see such a massive picture without getting lost in the details? The secret lies in the context window. Next, we'll see how it reads your entire infrastructure like an open book. Modern LLMs now feature massive context windows, often exceeding 200,000 tokens. This allows an AI to ingest the entire API documentation, the underlying source code, and even the network topology of a target company simultaneously. In practice, this means the AI can identify logical flaws, errors in the business logic that have nothing to do with bad code, but everything to do with bad design. For example, an AI can read your entire Swagger UI documentation and notice that a specific sequence of API calls, say, create user followed by cancel subscription, within the same millisecond results in a race condition that leaves the premium features active for free. This is a temporal logical flaw. A human researcher would need months to map these states. An AI does it in the time it takes to process a prompt. It maps the state machine of your entire application and looks for transitions that shouldn't exist. This level of holistic analysis is why your perimeter is more vulnerable than ever. Bridge, once the AI understands your logic, it starts seeing your infrastructure not as a wall, but as a series of predictable nodes, which is exactly what we'll explore in the next chapter, how AI sees your infrastructure. In the traditional security model, reconnaissance was a linear, human-driven process of trial and error. But by 2026, we are witnessing the rise of the agentic workflow in vulnerability research. Imagine a swarm of specialized AI agents, each with a narrow focus, one for subdomain enumeration using recursive LLM-based guessing, another for API endpoint mapping through semantic traffic analysis, and a third for service fingerprinting. These agents don't just run tools, they communicate with each other. If the recon agent finds an obscure staging server, the API agent immediately begins mapping its REST structure based on learned patterns from similar modern frameworks. This isn't just automation, it's coordinated intelligence that can map an entire corporate perimeter in minutes, identifying shadow IT that human researchers would miss for months. The perimeter is no longer a static wall, but a dynamic graph that AI parses with surgical precision. But how does this swarm actually interpret the code it finds? This leads us to a fundamental shift in how vulnerabilities are actually understood by machines. Let's look at the move from syntax to semantics. Historically, scanners relied on signatures and syntax looking for specific patterns like eval or strip. In the 2026 landscape, AI-driven research has moved towards semantic logic analysis. Instead of just looking at the characters in a line of code, the AI models understand the intent of the programmer. It analyzes the data flow across multiple microservices to identify logic flaws that bypass traditional WAFs. For example, it can detect an insecure direct object reference, IDOR, by noticing that the user-provided ID in a request doesn't match the session context, even if the syntax of the request is perfectly valid. This semantic understanding allows AI to find zero-click vulnerabilities in business logic, such as a multi-step checkout process that can be manipulated by reordering API calls. It's not about finding a broken character, it's about finding a broken thought. This shift renders most pattern-based defense mechanisms obsolete, because the AI isn't triggering a known signature, it's exploiting the very logic your application was built upon. But finding the flaw is only half the battle. The real disruption occurs in how these flaws are verified and reported without any human oversight. Once a potential logic flaw is identified, the AI enters the autonomous triage phase. In a fraction of a second, it spins up a containerized environment to replicate the target stack and attempts to generate a non-destructive proof of concept, POC. This isn't a human typing exploit strings. This is a model performing exploit validation through iterative reinforcement learning. If the first attempt fails, it analyzes the error response and refines the payload immediately. Once the exploit is confirmed, the system uses a fine-tuned LLM to write a professional, high-quality bug report, complete with CVSS scoring remediation steps and even a video-like walkthrough of the exploit path. This entire process happens with zero human intervention. For a bug bounty hunter, this means their time to report drops from days to seconds. For a defender, this means the window between a new deployment and its first targeted exploit is now practically zero. We are moving toward a reality where the volume of high-quality reports could overwhelm the most robust AppSec teams. But why is this speed so dangerous? Is it just about being fast, or is there something more fundamental about the scale of AI? Let's analyze the speed gap in the next section. The most jarring change in the 2026 security landscape is the absolute collapse of the time to exploit metric. In the pre-AI era, a human researcher might take 40 to 80 hours of deep work to fully map a complex infrastructure and identify a novel exploit. An AI cluster, operating with thousands of concurrent agents, can achieve the same depth of coverage in under 10 minutes. This creates a speed gap that traditional attack surface management, ASM, cannot close. When a human researcher works, they sleep, they take breaks, and they have cognitive biases. AI, however, maintains a constant, high-fidelity scan across the entire global IP space of your organization simultaneously. If you deploy a vulnerable staging server at 2 a.m., it is discovered and exploited by 5 a.m. This side-by-side comparison reveals that the defender's response time, which is usually measured in hours or days, is now fundamentally mismatched with the attacker's speed, which is measured in compute cycles. This disparity forces us to rethink everything from patch management to incident response. If the attack happens faster than a human can even receive an alert, who is really in control? Now, we must ask, what happens when this speed is combined with infinite scaling capacity? We have reached a point where compute is the new weapon. In the past, the limiting factor for a bug bounty hunter or a threat actor was human expertise. How many skilled people could they hire? Today, the limiting factor is simply the number of 100 GPUs they can lease. This infinite scaling changes the economic equation of cyber defense. When the cost of discovering a vulnerability drops from 5,000 in human labor to 0.50 in compute costs, the sheer volume of attacks increases by orders of magnitude. For a defender, this means your perimeter is being hit with expert-level probes millions of times a day. We are seeing a shift from quality vs. quantity to quality at scale. This isn't just about bug bounties. It's about the weaponization of compute to find every possible crack in your infrastructure before you even know it's there. The economic asymmetry is staggering. A defender must protect 100% of the surface area 100% of the time, while an AI attacker only needs to find one compute-generated logic flaw to break the entire chain. As we move into 2026, understanding this asymmetry is the first step toward building a defense that can survive the AI onslaught. In the next chapter, we will dive into the specific 2026 attack surface reality to see exactly which parts of your stack are most at risk. The perimeter didn't fail because of a missed patch. It failed because an AI understood the business logic better than developers did. In this landmark 2026 case, an LLM-based autonomous agent didn't just scan for known CVEs, it mapped the entire API graph of a major fintech platform. By analyzing subtle differences in response times and error messages across thousands of concurrent requests, the AI identified a deep-seated insecure direct object reference or IDOR vulnerability. It noticed that while the user ID was obfuscated, the resource ID followed a predictable pattern that allowed unauthorized access to sensitive financial records. Traditional scanners missed this because the syntax was perfectly valid, but the context was fatally flawed. The AI agent generated a multi-stage exploit that bypassed rate limits by rotating through thousands of legitimate-looking residential proxies, extracting 50,000 records before the first alert even fired. This represents a shift from syntax-based attacking to logic-based autonomous exploitation. But how does this scale across millions of endpoints without hitting a wall of cost? There is a dangerous misconception in the current security community that AI-driven hacking is too expensive or generates too much noise to be practical. Industry data and community analysis from platforms like Geek News tell a very different story for 2026. The cost of intelligence per token has dropped by 90% compared to 2024, enabling attackers to run sophisticated agents for pennies. We are seeing a mass automation effect where bug bounty hunters use orchestrator models to manage hundreds of sub-agents, each specialized in a specific technology stack. When an AI finds a potential entry point, it doesn't just blast it. It uses a chain of thought process to verify the vulnerability with a 98% accuracy rate before ever presenting it to the human researcher. This eliminates the low-quality noise that previously plagued automated tools. The reaction from the security community is clear. If you are not using AI to defend, you are being outpaced by attackers who use it to refine their targets. But wait, is it just the apps that are at risk, or is our fundamental network security infrastructure also crumbling? Traditional defenses like WAPs and IDS are built on the concept of signatures recognizing a known bad pattern. But how do you sign for something that changes every time it hits your server? In 2026, AI-driven attackers use polymorphic payloads. The A takes a standard SQL and injection or cross-site scripting attack and mutates it using thousands of different encoding schemes, whitespace variations, and logic equivalents that result in the same execution, but look entirely unique to a signature-based engine. While your WAF is busy looking for the string union select, the AI has already generated a variant using obfuscated hex codes and nested function calls that bypasses the regex entirely. This isn't just about speed, it's about the AI's ability to fuzz your defenses in real time, learning from every 403 forbidden response to craft the next attempt that gets through. We are moving from a world of static barriers to a world of dynamic, evolving threats. This way of bypassing is not an exception, it is becoming the rule. However, the biggest threat might not even be your main website. It's the assets you've completely forgotten about. The true Achilles heel of any enterprise in 2026 is its shadow IT and zombie APIs. These are the legacy staging servers, the forgotten microservices, and the temporary cloud instances that were never decommissioned. AI recon tools are exceptionally good at finding these. While a human might miss a dev subdomain from 2022, an AI crawler will find it via certificate transparency logs, DNS brute forcing, and historical web archives in minutes. Once found, these forgotten assets become the perfect staging ground for a breach, because they often lack the latest security patches and monitoring agents. They represent your legacy debt, and in the age of AI bug bounties, this debt is being called in. If your asset inventory isn't 100% accurate, the AI will find the 1% you missed. This is the reality of the 2026 attack surface. It is wider, more complex, and more transparent than ever before. Now that we've seen the devastation, we must build the shield next. We move to the AI resilient defense framework. In the landscape of 2026, the traditional fortress model of security is completely obsolete. As an architect, you must transition to a liquid defense stack where the perimeter is defined by identity and real-time behavior rather than static IP ranges. This new stack begins with AI-driven observability at the core, utilizing eBPF-based deep kernel monitoring to detect anomalous patterns that traditional EDRs might miss. On top of this, we layer an adaptive policy engine that adjusts access rights dynamically based on the risk score of the current session. For example, if an AI-driven agent starts scanning internal API endpoints at a speed no human could achieve, the system should automatically transition that session into a sandbox environment. This isn't just about blocking, it's about Zero Trust 2.0, where every single packet is validated against a machine learning model trained on normal operational traffic. We must move from detect and respond to predict and preempt. But how do we act on this massive influx of telemetry data before the AI-armed attacker exploits the vulnerability? The answer lies in the speed of the remediation loop. Closing the gap between vulnerability discovery and remediation is the single most important metric for a 2026 blue team. We call this AI side speed. When an AI-assisted bug bounty hunter submits a complex exploit chain, your internal defense systems must be capable of autonomous patching. This process starts with AI-driven triage, where an LLM analyzes the submission, recreates the exploit in a secure digital twin environment, and then suggests a code fix. By integrating this with your CI/CD pipeline, the Blue Team AI can run automated regression tests on the proposed patch and deploy it to production as a canary release within minutes, not days. We have seen cases where the mean time to remediate, MTTR, was reduced from weeks to less than an hour using this autopilot for AppSec approach. However, this level of automation requires rigorous validation to ensure the AI-generated patch doesn't introduce new logic flaws or performance regressions. Technical resilience is only half the battle. The other half is the legal and ethical framework that keeps the researchers on our side. As we move into 2026, the volume of AI-generated bug bounty reports will increase by an order of magnitude. This necessitates a fundamental update to your corporate bug bounty policy and vulnerability disclosure program, VDP. We must clearly define the boundaries for safe harbor when researchers use automated agents. Your policy should mandate that researchers disclose if AI was used to identify the bug and provide the prompts used for reproducibility. From a risk management perspective, the biggest challenge is the AI noise of flood low-quality or hallucinated reports that drain your team's resources. To combat this, modern programs are implementing proof-of-work requirements or reputation-based reporting limits. Legally, you must ensure that your agreements protect intellectual property if an AI researcher's tool inadvertently ingests sensitive proprietary code during the scanning process. This governance structure works on paper, but a professional engineer must look beyond the rules to the core philosophy of risk. In the field, being a professional engineer means more than just knowing the code. It's about taking ethical responsibility for the systems we build. In the age of AI, this means balancing the drive for rapid innovation with a non-negotiable commitment to public safety and data integrity. We often see organizations chasing AI-first features while neglecting the underlying security debt. The PE perspective dictates that security is not an add-on, but a fundamental quality attribute of the system. We must adopt a security-by-design mindset where AI defense mechanisms are baked into the architecture from day one. Risk management is no longer a checklist. It's a living, breathing process of continuous verification. As we conclude this framework, remember that the most sophisticated AI is still just a tool. The judgment, ethics, and strategic vision of the human architect remain the final line of defense. This framework sets the stage for our final chapter, the ultimate checklist every security architect needs for the 2026 landscape. If you treat your AI endpoints like standard REST APIs, your perimeter has already failed. By 2026, the speed of automated vulnerability research means that a static firewall is practically invisible to an AI-driven attacker. Within the next 30 days, you must transition from traditional DWAF thinking to an LLM-aware gateway architecture. This in implementing semantic rate-limiting blocking users based on the intent of their prompts rather than just their IP address. You need to verify that your system prompts are not being leaked through indirect injection in your RAG pipelines. Hardening your API authentication is only the baseline. The real battle is in the context window. Your first action item is to audit every point where external data touches your LLM. If you aren't monitoring for jailbreak as a service patterns in your logs today, you are already behind. But wait, is a one-time audit enough to survive the next generation of autonomous exploits? Security is no longer a state you achieve. It is a living posture that must evolve faster than the agents attacking it. As we look toward the 2026 landscape, the traditional boundary between attacker and researcher will blur as autonomous bug bounty agents scan the globe 24/7. To survive, your defense framework must integrate continuous learning cycles where every blocked attack is used to fine-tune your guardrail models in real time. We are moving toward a zero-trust AI model where no prompt, even from an internal user, is considered safe until it is sanitized at the semantic layer. This marks the end of our deep dive into why AI bug bounties will break your perimeter. The tools are changing, but the core principle remains. Visibility is the precursor to security. Now that we have established the framework, The next step is applying these defense-in-depth strategies to your specific production environments. The era of static defense is over. The era of autonomous resilience has begun.